Of August, and we're going to continue working with the method of joints. We're using this example problem, 6.5, from the textbook of DOS, which is a statics textbook, and we're going to continue with our work to find the tension or compression in the structural members. We're going to chase the whole joint, we're going to chase the whole structure and get all of the reactions. Now, what I have just done before we turned the camera on was to check to make sure that the reactions that I solved for on Friday are correct as far as the authors are concerned. So I checked this, it is negative 30. I checked this, it is 21.25. And I checked this, it is negative 16.25. So all my reactions are correct, which means we can proceed through and find the rest of it. All right, so the first thing I'm going to do, because when we do the method of joints, we only have two equations. We have the forces summed in the y direction equal to 0 and the forces summed in the x direction equal to 0. That means that we can only work with a joint that has two unknowns. And when we start with a joint that has two unknowns, we can then work our way up, which is the part that I'll show you today. But if we start here at joint A, you'll see that we have the known reactions, because we've just solved for them, RAX and RAY. And then we have two unknowns if we consider A to be the joint. We have the tension or compression in structural member AC and the tension or compression in structural member AB. So the way that we do the method of joints is to draw the joint. I don't really like this pen. Let me get a different one here. If you can see this is going to be blue. Tell me if it's difficult to see. Okay, this is my joint at A, and this is the process. We always start with some joint that has two or fewer unknowns. We know that I have the reaction at A in the x direction, which is equal to negative 30 kips. I'm just going to write kips up here so I don't have to keep writing kips. And you remember kips is a kilopound, so we're talking about 1,000 pounds. So the reaction at A in the x direction is negative 30,000 pounds. The reaction at A in the y direction, downward, so the reaction at A in the y direction is negative 16.25 kilopounds. And we don't need to mess with the reaction at B because we're just talking about the joint at A. We then have AC, which has to be directed along that structural member. And we have AB, which has to be directed along that structural member. So we know the geometry of those two. We know which way they work. However, we don't know whether they're in tension or compression, which is the next part, and we don't know their magnitude. So the first thing I do before I begin my analysis is I take a pause and I look and I see this one is pulling to the left and this one is pulling down. If I look at these two structural members, this does not have a y component, does it? AB does not have a y component. That means that the only y component to offset this is in AC. So if the reaction A in the y direction is pulling downward, what direction does AC have to be? Does it have to be, sorry? Upward, absolutely. And so we know that my arrow is going to look like that. Now, if I didn't know, I could just make a supposition and it would come out, but I'm going to have fewer weird things if I can make that determination. Okay, now as far as this goes, AB, I have a component going to the left in A and the component going to the right on AC. So I really don't know if this one is going to be to the right or to the left, do I? But I'm going to have to make a supposition, and it may come out to be negative. So I know that this is correct. I don't know if this is correct or not. So we're going to do this. All right, so everything that goes into the joint has to sum to 0. The summation of forces in the x direction going into joint A have to be 0, and the summation of forces in the y direction going into joint A also have to be equal to 0. So I can go ahead and write equations for this based on my knowns and unknowns. In the x direction, I have negative 30 kips. RAY and AB, AB has a an x component. Actually, the entire thing is in the x direction. And AC, part of it, is in the x direction. And the way I have it is positive. So it's AC, not the entire force in AC, but the x component of AC. Those three things added together equals 0. And in the y direction, I have negative 16.25 kilopounds, and I have positive AC in the y direction. Those are the only two y components I have, and that's equal to 0. So if I can determine my geometry of joint AC, which of course I can plug in here and solve immediately for this value of AC. All right, so let's take a look at what AC looks like. Going back to my original drawing, I see that from A to C, the horizontal distance, well, that's weird. I'm trying to think about this. This 10 feet goes all the way up to point E, doesn't it? So if I look at my triangle that AC is built on, A to whatever point this is, E, here's A. This is the geometry of the actual structure member. Up here to point E, this horizontal distance is 10 feet, and the vertical distance is 40 feet, isn't it? So I think last time I had thought that this distance was 10 feet from here to here, but it's not. I see from the drawing that it's actually the entire height of that picture. So that means that my angle at A is significantly different. So what is my angle at A? Well, I have an opposite side and an adjacent side. So opposite adjacent gives me a tangent. So I can say that 40, opposite over adjacent, 40 feet over 10 feet is the tangent of A, or that A, the angle at A, is the arc tangent or inverse tangent of 40 over 10. And so the angle at A is what? And I said before, like I said, I apologize. When we started this last time, I misinterpreted the picture. But now this is the correct interpretation of the picture. So we need the inverse tangent of 4 is what it amounts to. And in degrees, please.
75 to
9.6, like that? Okay, and you can see from this picture, that actually looks more realistic, doesn't it? If you look at that, that doesn't look like a 56-degree angle. That looks quite a bit higher than that. So this is the way we go. All right, so now that we know that angle, we know that the force has to be directed along the structural member, we can determine what the AC component is in the y direction. Or B, that should be C, sorry. So from A to C, in the y direction, we're looking at the opposite to that angle over the hypotenuse, which is sine, correct? So minus 16.25 kilopounds plus the entire force in AC times the sine of that angle equals 0. So if I want to solve for the magnitude of AC, I bring 16.25 over to the other side, which is positive when I change sides of the equal sign. Divide by the sine of 75.96 degrees, and I'll get a magnitude of AC. The entire thing is, this should be smaller than 1. And so if I divide that, it should be a little bit bigger than 16. So 16.75. Is that correct, Jess? Okay, good. So AC is 16.75 kips. That means I have my first piece of information, right? All right. Now, the next thing I could do is solve for AB, since I have this x equation. So I'm just going to bring this down over here. And I'm going to say, just repeat, the sum of the forces in the x direction going into joint A equals 0. Negative 30 kips plus AB plus, the way I have it drawn, and would always stick to your picture, even if you don't know if it's right or wrong. Stick to your picture. If you don't stick to the way the picture's drawn that AC, the component of AC in the x direction is positive. So make sure you do that. AC in the x direction is the cosine of this angle. Because cosine is adjacent over hypotenuse. Cosine of 75.96 degrees. Those three things added together equals 0. We know that AC is 16.75 kips. So I'm going to put this on, leave AB on the left-hand side of the equation, bring 30 over to the right-hand side, bring AC, which is 16.75, reduce it to, or project it onto, I should say, the x-axis, and then I can solve for AB. And this is where we'll find out if we're correct or not. Now, we are going to be correct, but if we were not correct in making our assumption of our direction, that would be reversed. Okay? We'd get a negative, is what I'm telling you. So what is the magnitude of AB? Or AC? AB. Oh my goodness. $25.937. Let's just do that. Let's get everything else in 2 decimal places. Okay. So when we have our answers for a problem like this, we will write, because the answers are what are the tensions, or what are the magnitudes of the forces in each of these joints, and is it in tension or compression. So what we do at the end is we draw a little table that looks like this. AB equals, AC equals, and then we'll do all of the other structural members as well. We know that the magnitude of AB is 25.94 kips, and that the magnitude of AC is 16.75 kips. And what is left to be determined for us is whether that force is in tension or in compression. Well, this presents a couple of really interesting ideas, because we can't use positive and negative to determine tension or compression. What we use is the idea of whether the force is pulling on the joint or pushing on the joint. Okay? So I have to go back to our original picture, and we decide, since our arrows are correct, if you think about the joint and you think about what AB is doing to it, is AB pulling on that joint or is it pushing on the joint? It's pulling, and AC is also pulling on the joint, right? So that means that those are both in tension. All right. So here comes the next interesting part. First of all, yay, we've already got, this is like 70% of the work we need to do. Here's the other thing. When we move across that structure, let me find my original picture again. Let's say that the next joint we want to analyze is B. Now, the tension in AB is going to be the same at A as it was at B. So we can use the value that we found here, right? And we have the reaction at B in the y direction, so we just have 2 unknowns. So I'm going to draw this joint B, but you'll see something that we have to make sure we do correctly. Here's our joint at B. We know that RBY looks like this, right? And once again, we're in kips. And we know that AB is horizontal. But what I want to show you is, if you look at this picture, AB is pulling on this joint. That means it's pulling on this joint as well. So in other words, it goes to the right here, but it goes to the left here, because it's pulling on both joints, isn't it? If it was going in the same direction, what would happen to that structural member? Fly off into the ether. It would no longer be a structural member at all. It would just be a projectile. So this is the deal. So AB, which has a magnitude of 25.94 kips, is still the same magnitude, and it's in tension, which means that from a statics point of view, the direction reversed. It goes to the right from joint A, goes to the left from joint B. It's the same force though. Okay? Oh. All right. So let's take a look at joint B then. We have these two knowns. We then have BC. Let me put this here so those of you that don't have it printed off. We have BC. Oops, let's try again. BC, which goes like that. And then we have BD, which goes like this. So this is BC, and this is BD. All right. Now, if you look at AB, which is the only known goes to the left, that means that at least one of these is going to have to go to the right, isn't it? And this goes up, so at least one of these is going to have to go down. So my advice to you would be to draw both of them going down to the right. You don't have to, but just stick with that picture, and then if you get a negative, you'll know you've chosen incorrectly. Okay? So we do the same thing at joint B. Summation forces x equals 0. And I'm going to put it down here because I know I'm not going to have enough room. Summation forces y, I should say, going into joint B, also equals 0. Okay? So what do we have in the x direction at point B? We have a negative AB, which is 25.94, and this has no x component. We have a positive BC in the x direction and a positive BD in the x direction. Those three things sum to 0. And in the y direction, AB has no component in the y direction. So we just have a positive 21.25, which is my reaction. Then we have negative BC in the y direction minus BD in the y direction, according to my picture, equals 0. So I have two equations and two unknowns, but we don't have one isolated in an equation. So that means we're going to have to get our geometry, get our trig, get our angles. They're two different angles. And then we're going to have to solve them simultaneously to get BD and BC. Or we can solve for BC and substitute it in, or whatever technique we'd like to use. All right, so let's take a look at joint B and what BC looks like. This is kind of bothersome to me. Oh, that's all right. All right, so from B to C, this angle, what do we got going on? Oops. We have 20 feet in height between B and C, and we have some distance in the x direction. Okay, if the entire distance from A to E is 10 feet in the horizontal direction, this distance is the same, so by similar triangles, does it make sense that that vertical distance would be 5 feet, or the horizontal distance would be 5 feet? So in other words, the distance from here to here is 5 feet, so the horizontal distance from C to B is 35 feet. Does that make sense? Okay, just wanted to double check. So let's draw BC. The horizontal distance is 35 feet, and the vertical distance is 20 feet. So the first thing is we need to determine what is my angle at B. Well, for BC, because there's two angles here. But actually BD is going to be the same as AC, isn't it? So we already worked that one out. Just by symmetry, we know that the angle here at B of the entire structure is going to have to be the same as we just found at A. So this is really the only one we have to work out. So the angle at B, then, once again, we have opposite, adjacent. It's going to be the inverse tangent of 20 over 35. Do I have all that on my page? Okay, so what's my angle at B? 29.74 degrees. Very good. And now we know the other angle, if we're looking from A to B up to D, has to be the same as it was on the other side here at A. And so that's the 75.96. I don't have a good label for it the way I've drawn it, but there we go. All right, so we're going to do the same thing here. We're going to say negative 25.94 plus BC in the x direction is going to be the cosine of this angle plus BD in the x direction, which is going to be times the cosine of this angle, equals 0. And over here, BC in the y direction is going to be the sine of that angle. And BD in the y direction is BD times the sine of this angle. And that equals 0, which I forgot. I put that right there. All right. So my preference, we need to solve these simultaneously. If you have a solution, like if you have a 2-equation, 2 unknown solution algorithm on your computer, on your calculator, you can use that. Or we can do it the old-fashioned way. We can solve for BC or BD and then substitute it into the other equation. So let's go the long way, and then if you can do it a shorter way, that's fine. Let's go ahead and just solve for BC right here. And this is randomly chosen. So I'm going to pull BC over here because it's negative on the left-hand side. So I get BC is equal to something divided by the sine of 29.74. And that something is 21.25 minus BD times the sine of 75.96. Okay? I'm just trying to decide if I want to do this. I mean, I do want to do this. I just want to know would it simplify it if we turned this into numbers? In other words, let's split this up. Let's split that denominator. 21.25. Divide that by sine of 29.74. And subtract from that the sine of 75.96 over the sine of 29.75 multiplied by BD. That's going to equal BC. So let's get this number and then the coefficient of BD, and we'll have a simpler expression for BC. And then I'll substitute it into the other equation. But what is 21 point, oh, go ahead.
That should be 42.83.
This?
Yeah.
Great. And sine of 75.96 divided by the sine of 29.75. Like that?
Yeah.
Okay, super. That's equal to BC. So you can probably also understand why we don't have a ton of problems. Why if you get like 3 problems in a homework set, you're like killing yourself to get it done in 2 days. Yeah. So just letting you know. So we have, let's see, so this is equal to BC. So I'm going to substitute that into my x direction equation. And so I'm going to have negative 25.94 plus, instead of writing BC, I'm going to write 42.83 minus 1.955 BD. That quantity times the cosine of 29.74 plus BD. We'll just simplify this before we pull that out. Cosine of 75.96 equals 0. So the good news is I now have one equation and one unknown. So I'm going to be able to solve for BD. But we need to do a little bit of simplifying first. So let's go ahead and do this in a couple steps. Negative 25.94 plus, let's distribute, take the value of the cosine of 29.74 multiply it by 42.83 and tell me that value. Perfect. All right, now cosine 29.74 times negative 1.955, which will be the first coefficient of BD.
Negative 1.697.
Okay, we'll have to keep 3 of those just for now. All right, and then let's just find out what is the cosine of 75.96. So that just numerically, so that we can get that BD.
0.24.
Maybe one more decimal.
2.5, so 3.
2.5, like that?
Yeah.
BD. Okay, those things added together equal 0. Okay, now the reason I waited before, the reason I did this simplification step was because what you can see is that on the left-hand side of the equation, BD is going to be negative, isn't it? So what I want to do is to take, well, I guess I would say this minus this, and then bring it over to the other side as a positive. So in other words, BD times, numerically it would be 1.697 minus 0.2425. Is that right? Is it 1.455? Okay. And that's going to be equal to the numbers 37.19 minus 25.94. Like that? Okay, good deal. Now we're ready to solve for BD, because all we have to do is divide both sides by 1.455.
7.73.
All right, very good. And then we can go back to our equation for BC, our most simplified equation, which is right here, right? And we can say then 42.83 minus 1.955 times BD, which is 7.73, equals BC. All right, very good. So what does that mean? In our table of answers that we will have at the end, we will then say BD is equal to 7.73 kips, and BC is equal to 27.71 kips. And then we need to go back and look at the joint to determine what the directions are. Okay, look at BC. The arrow's going down. Is it pushing on the joint or pulling on the joint? That's pushing. That's exactly correct. So BC is in compression. BD, compression. Very, very good. All right. So what questions do you have so far? Okay. Without questions, what I'm going to show you, and I've put this up on the Moodle page for you, but the way that they've organized the truss is to just draw basically not a free body diagram, but a simple line truss. They've eliminated all of the extra sketchy things, and they've basically written every force, and then whether it's in tension or compression. You'll also see that EF is a 0-member force. Now, you can solve that, and you can see FD is a single-member force also. You can kind of see that here if you just look at joint F. The reason is this has to have a vertical component, and there's nothing to offset it, is there? So there's no vertical component. There's just one vertical component. So in order for this truss to stay still, it has to be 0, doesn't it? And so once that becomes 0, you can see that the entire thing is 0, and then the horizontal component is also going to be 0. And so that's a 0 force. So what that really means is this little chunk of the triangle up here, for this loading condition, is doing nothing. There is nothing going on for that particular structural member, but it's still there, taking up space. So making it look more symmetrical and so forth. So anyway, so this is just the way that the authors here organize the final answer, and then I just like to organize it in a table. But either way is the same information. So because we only have 13 minutes left, I'm not going to keep chasing this. I just want to talk about technique. But what we would basically do after we got to that point, let me go back to my original picture. Okay. So then we've analyzed here and here and here. So we have, let me get a red pen. We know the force in this, and this, and this, and this. That means if you look here, if you went to C, we have 1, 2, 3 unknowns, so we can't do that joint. If we go here, we have 1, 2, 3 unknowns, because even though I just told you that this one's 0, we don't know that yet. So we can't really analyze either of these joints. We can't analyze this joint either, because we have 3 unknowns, so we have to start here. And we go 0, 0 after we go through the analysis that we've just gone through. Then when you know this is 0, you have 1, 2 unknowns, so you can analyze joint D. Then you'll have over here, oh wait, I was just looking at something. On C, we have this and this. So we could have gone straight to C. I apologize for that. We know this and we know this. So here at C, we just have 2 unknowns. So we could chase this up to C, do the same thing. And then we'd have this one, so we could go to joint E because we only have 2 unknowns and so forth. So that's kind of the trick.
Could you just start the problem out by finding those values that are 0?
Yes, absolutely. And it's an excellent question. It's also a really good analysis technique because you can simplify things for yourself really quickly by doing that. If you just take a minute and go,
there's no forces acting on that. So
right. Those are zeros, so I've got a lot more places to start and not so much work to do. Another thing you can do that will simplify your work, and we did it just a tiny bit here, is to just look at symmetry. Like, for example, let's take a look at this. This is one of the homework problems. If you look at this truss, okay, we have 4 feet, or 4 meters, 4 meters, 4 meters, 4 meters, B, C, and D, all right, A and E, 20, 20, 20. All of these forces are the same value. All of these distances are the same. That means that everything on this side of the truss is going to look like everything on this side of the truss. Okay. Now, if one of these forces, if this were 40 kilonewtons, that would not be the case, right? Or if one of these distances was different, that would not be the case. But when you have geometric and loading symmetry, you can eliminate, like in this case, half of your work by doing that rather than like doing all the work and then going, wait a second, this looks exactly the same as the other one, which is also fine. I mean, sometimes you do that, but sometimes you get in a rut and you just sort of do that. But if you just take a minute and look at that, like Jess was saying, look for a 0 member, look for symmetry, you'll be a lot better off. So with that, let me just give you a couple homework problems and we'll call it a day. We'll actually get to go home early today. What do you think? So on the handouts, what I would like you to do is this problem that I just talked about, 621, which is an excellent problem. And then let's do something with quite a bit less symmetry. I know. But let's do, I want to do 617. Okay? So this one, which is just the same thing. Find the loads and whether they're in tension or compression of each of those structural members. So our homework tonight will be just those 2 problems, both of which are up on Moodle. And then after we get done with that, we'll be ready to get started doing stress. We'll go back. This is not a review, but this is to make sure that everybody's on the same page with statics. because this will be a necessary skill in order to start doing normal stress and shearing stress. And to be honest with you, this is the hardest part. So once you can do the statics, and this is called indeterminate. It's an indeterminate structure. You'll be ready to move forward really quickly.
So this is all Moodle, you said?
Yes, it is. Yeah, let's take a look at Moodle. Make sure I'm not telling you stories, because once in a while I forget to do stuff. Let's take a look. You guys can't see this. Hang on, let me pull up presentation, Podium PC, Moodle. All right, there's my vodcast, the member of joints handout. Okay, so I start here. Make sure I put the homework problems on. This is the directions, and there's the problem that we just worked. And okay, here we go. So the homework problems, I have 10, 11. And here's the one. Yeah, there's the first homework problem right here. And there's the second homework problem. Okay. So everything's on Moodle. All right. All right, gentlemen, thank you so much. And I'm going to stop streaming now. And we will pick up where we left off on Wednesday. But